Hello all, welcome back. So in the last tutorial we have completed our block design for interfacing video with the VGA interface of ZedBoard. So as I mentioned before, only thing that is left is giving the video input. So we are going to make a module which will generate some video signals which we will transmit over the VGA interface. Now ideally that module you may have to design as a separate IP, maybe in a separate project, and add it here. But I wanted to show one more feature of Vivado. So in order to show that, I'm starting my module design in Verilog in the same project itself, okay, where I already have the block design. So I'm starting a new Verilog source, and let's call it data gen.v. This module is going to generate some data which we will send it or VGA. Okay, so first we have to make the interface. So we have the clock, 148.5 megahertz clock. We have the reset signal. Now output, okay, we need to connect it here. So we have the standard AXI interface. In addition to that, we have two additional signals: the start of frame SOF signal and end of line signal. Okay, so let's say output 7 down to 0 for data. We have output for data valid. We have input I data ready. We have, in addition to that, we have O start of frame, and we also have O end of line. Okay, so that's the interface. Now we need to generate the signal. So the easiest way is to write a small state machine. Always at such high clock. If we are in reset, we will go to idle state. Remember, this is AXI reset, so it should be active low signal. So begin and let's say state is in idle state. Okay. Okay. So how the data should be transmitted? So as for protocol, when you start the first frame, you need to make the SOF start of frame signal high. Okay, so let's make start of frame signal high. Along with that, first pixel of data should be also set. Okay, so along with that, I'm going to make O data valid high. So the actual data we will generate it separately after this. Okay, so we are making these two signals high, and we will go to the next state. Let's call it send data state. Okay, send. Now we need to follow the AXI protocol here. That means there is a possibility the AXI4 video converter, he may put some back pressure. He may say like he is not ready to accept data. So you need to keep this SOF and data valid high as long as the data ready becomes high. Okay, so if the ready signal becomes high, that means he is ready. You can make the SOF signal low, but data valid I am keeping it high because now we are starting to send data and we are planning to send one entire line of data. Okay, now to check whether we have finished sending one entire line of data, we need some kind of counter. So let me call it something like line pixel counter. So this counter will count how much pixels I have transmitted for this particular line. Okay, so let's initialize that to 0 when we are under reset state, and we need to declare it. Okay, so we are not much worried about the resource utilization and all. We can directly declare a 32-bit pixel counter, so initially to a 0. So each time he says he is ready, that means, remember, what data value is already high, so data ready high means a successful data transmission happened. Okay, so I will increment this pixel counter. So now on every clock I am transmitting a new data, and I am incrementing my counter only if that data is accepted by the video converter. So this keeps on happening until I finish sending one entire line, and when I finish sending an entire line along with the last pixel, I need to make end of line signal high. Okay, so I need to compare if my pixel counter with some value which indicates like I have finished it. So that we need to declare. Okay, we'll declare it. Let's call it line size or something. Line size -2. Okay? That means we are transmitting the second last pixel on this clock. So along with that, we need to make end of line signal high, and on the next clock we have to make it low. Okay, so we'll make O end of line 1 we are making, and we will go to the next state, and let's call it something like end line, because we need to make sure this EOL is also seen by the video converter for 1 clock cycle. Okay, begin end. So this we will declare. Tick define line size. We are using 1080p, so one line size is 1920. Okay. So we made the signal high, and in the next state, the end line state, again we need to check whether he accepted it. So if I data ready, I can make the signal back to 0, and I can reinitialize my pixel counter also back to 0. Okay, so everything looks fine. Now we need some way to decide whether I finish sending one entire frame or not. For that we will have to use another counter. Okay, so based on that I will have to go back to idle state and again make this SOS signal high. If I haven't finished one entire frame, I just finished some line in between, I will have to go back to send data state and again start sending the next line. So to distinguish between these, I will need some kind of counter. So let's call it data counter. Again, let me declare it as integer data counter. Again, we can initialize it to 0 when reset comes, and whenever we send a valid data, we will increment it. So here we are sending valid data here, okay, because ready is high. We are incrementing it. So here also there is a valid data transmission. So here also we are incrementing it by 1. Now we need to check whether I am sending the last data or not. So for that I will compare if my data counter is same as my frame size. Okay, so let's define our frame size. So tick define, let's say, okay, frame size is 1920 times 1080. So when we are sending the last pixel, so frame size -1, we will check. That means on this clock I am sending the last pixel. Okay. If they are matching, that means I will go back to idle state. I will make my data valid signal 0 also, because I'm going back to idle state, and I will start a new SOF and start transmission from there. 1 P 0, and I can also reinitialize this to 0. This you can do either here or you can do it in the idle state also. Okay, both are fine. Else, that means I finished sending a line, but that is not the end of the frame. Just go back to send data state and continue sending next line. Okay, so that's it. Now we have to declare everything. So state, we have 3 states, so it should be 2 bits. Red 1 down to 0 state. We have local param idle 0. We have send data, let's say 81, and end line, let's say 83. And end of line, okay, SOF, they are all inside always blocks, so we need to make them rich type. Okay, so that part is also done. Or data valid also. They should be all rich type. So this also we need to initialize under reset. All the control signals, output control signals should be initialized inside the reset. So this also start of frame and end of line also. Okay, so that's it. Now the only thing that is left is assigning the actual data. So my plan is to create some vertical color bars on the screen. You might have seen that is the standard video testing pattern. Now I'm not planning to have like 7 or 8 vertical lines which you usually see. We just want to test the minimum functionality. So I'm planning to have 3 vertical lines. Let's say 1 red, 1 green, and 1 blue. Okay, so 1/3 of my screen should be red, 1/3 green, and 1/3 blue. So for that, what can I do? So we have the data here, or data. Okay, so I made the mistake. This is 1 byte, but we have 3 of them, so it should be 23 down to 0. Okay, yeah, 24 bit data. So out of this 24 bits, the lower 8 bits, they represent R, then G, then B. So when I'm sending a line data, for 1/3 of the line data, I'll make only the R signal high. Blue and green, I will keep it low. For next 1/3, I will make G high, other two low, and next 1/3, I will make B high and remaining low. Okay, so that's very straightforward because we already have a counter which counts like how many pixels of this particular line has been sent. So I can take advantage of it and I can just use that to create this output. Okay, so I'm just writing it as a combination circuit. So I will say like if line pixel counter, if it is between 0 and 1/3. Okay, so remember our width is 1920, so we have 1920 by 3, 640. Okay, so if this counter is between 0 and 639, that is like 640, I'll make my OData. I'll make my OData like this. Yeah, so we have 24. This is 1 byte, 2 byte, and 3 byte. That means my R value is FF maximum, G is 0, E is 0. So same style we can do it. Else if it is between 640 and 1280. We will make G high F00, else final case make blue as high. So although here we are using 1 byte for each color component, finally only the lower 4 bits will be going out of the board, because each color component which has only 4 bits on the VGA on ZedBoard. Okay, so we need to make this also as rich type, and that's it. So that completes the design. No syntax errors. Okay, now the interesting part. Now I want to use this module in my block design. So as I mentioned before, you may package it into an IP and import your IP, things like that. But Vivado also supports this drag and drop. I can simply drag and drop this module here, and you will see he automatically converted into a block. Okay, and he's showing like RTL, which is basically saying, okay, this is a RTL design. This is not in IPXAT format. Okay, the only issue, I won't call it issue, you won't be able to group signals together. Previously, if it is AXI stream, I can group all the AXI stream signals together and just drag and drop and connect them. But here you cannot do it, they all remain separate. So we have the data and valid here because they are output, and ready here because that's an input. Okay, so run automation, he will connect the clock. Okay, so this we have to do interface by interface. So this O data we will connect to this video T data valid to the valid here, and ready to here. Start of frame is configured as T user. You have to look at the data sheet, and end of line is configured as T last. Now the reset we can connect here. Looks good. Let's check whether any error is there. Okay, no errors are there. So let's do one thing. Let's go ahead and simulate the design. You can simulate this entire design because there is no processor involved. If the PS part is involved, you won't be able to simulate that processor part, because I guess till this point Xilinx, they haven't provided the complete bus functional model for the PS part. But since here there is no processor, you can completely simulate it. The only input expected from you are this clock, which is 100 megahertz, and this reset, which is active low, and you can see whether these output video signals are coming. Okay, so let's go ahead and create HDL wrapper. Okay, and after that we can simulate. So in settings and simulation, top module name, okay, we need to change. We need to give this as the top module name. Okay, you'll see like this data gen, it is not in the hierarchy till now, but once he generates the output products, it will automatically go inside your system. Okay, so run simulation, run behavioral simulation. It may take some time because we have many IP cores, and he has to generate the simulation model for each of them, and even the simulation will be slightly slower because of the presence of many IP cores. Okay, he has completed the compilation, and let's add signals to the waveform. So these are our top level signals, but let's also see how signals are going into the IP core and also we can just expand. Let's see our clock gen circuit. Okay, whether he's giving proper 148 megahertz, we can see. So this is our clock gen, and this is our data generator. This is our timing control generator. This is our AXI4 stream to video out. Okay, so we have added all of them. Now let's restart simulation. Okay, so let's apply the input clock, system clock. Okay, system reset. 1.0. We have to give 100 megahertz and reset. We need to keep reset low and let's run for like 1000 nanosecond with reset. And if you look at the clock gen, yeah, you can see the output clock is not present. Okay, so ideally other modules, they should be kept under reset as long as the output from the clock gen is not stable. Okay, so for that we could have used the locked signal coming out of the clock gen. That is a good practice. You need to combine this external reset with that lock signal to generate some internal reset which should go to all the peripherals. But we haven't done it, so let's do one thing. We need to keep everything under reset until the clock out becomes stable. And here you can see, so there was no clock signal. Initially there were some pulses, you can see, but then it became low, and from this point he locked. Okay, so he will constantly give 148.5 megahertz from this point onwards. Okay, so once every module starts to get the clock, we will apply the reset. So you can see it took approximately 3.4 microsecond for the clock to stabilize. So when we use it on actual hardware, this is a very small duration, so we will keep the reset button pressed for 1 second or something to make sure clock is stable. Okay, so after that we can make reset high and we can run the simulation continuously. Now it will take a long time for the output to stabilize, you will see. So you'll have to run maybe like 100 nanosecond, sorry, 100 millisecond to see some proper output. So it may take a long time, but you can see like our data generator, he's generating data. You can see it. Okay, he made the SOF signal high here. You can see, yeah, we made the SOF and valid high here, but the ready signal is low on the next clock. So that's why we kept on asserting it until he became ready. Okay, so from now this point onwards, data transfer is properly happening. So here is our first line, we finish. Here we finish second line, so on and so forth. Okay? But if you look at the output, there is no data, there is no synchronization signal, because the AXI video out module, it will take some time to internally synchronize things, because the video interface and the timing generation interface, these are two separate interfaces. So this guy, he has some internal state machine. It has to find some synchronization before he starts giving out the actual data. So here there is a signal locked here on the block design. Also you can see this signal, we didn't use it. So this signal will become high once he locks between the timing control signal and the video signals that we are providing. After that he will start to give the final output. you should be able to see the RGB output coming here, as well as H-Sync and V-Sync. So let's wait. You can see, like, after some 110 millisecond, now the output is coming. Okay, you can see the first vertical sync is coming here, then there are a lot of horizontal syncs here, and you can see the RGB values are going like F, R, G, B. Only one of them is F, other two are 0, right? So it's working like that. And if you come to the video IP, you can see the locked signal that is coming around at 94 millisecond. It's basically saying the IP has locked between the timing control and the video signal, and he is going to give the output. And here there is some status. This is coming from his internal state machine. So if your IP is not working in simulation, you have to check the data sheet and you have to check the status bits, and it will say like what is going wrong. So usually the problems are like the resolution that you specified is not matching with the incoming video. Okay, you set like you aligned with this say 1090, but only 1089 pixels are coming. So in that case there will be some error, things like that. Similarly, there are underflow overflow signals here. These are coming from the internal flip-flop. So if your incoming video frequency is less than the pixel clock frequency, the underflow may become high. If that frequency is more, overflow will become high. So that is applicable only when you're working asynchronously. That means your video signal clock is different from the timing control clock. Okay, so otherwise it is working. Now we can synthesize, implement it, and test it on hardware. But the only issue that I faced was, anyway, as per VGA standard, when you have horizontal or vertical synchronization, all the output data, all the RGB channel values should be 0. But here that is not coming like that. Okay, logically, I don't think that is necessary also, because this is basically saying there is a sync pulse, so the video is not valid. But when I tested on real monitor, it was not working. Okay, so what you need to do is, whenever there is any synchronization signals coming, these values should be made to 0. That our IP is not automatically doing. So in our block design, what you need to do is, we need to put some kind of multiplexer here whose output will be 0 whenever there is no valid signal, or whenever the synchronization is happening. Otherwise, he should send these signals as output. So the easiest way to do that is, there is a signal coming from here, video active video. Okay, so this signal will become high whenever there is a valid video data here, otherwise it will remain low. So using that, we can build some kind of multiplexer which will choose between 0 or this signal based on this control signal. Okay, so let me, same way I made the data generator, this is a small multiplexer. So let me create it here itself, mux.v, let's call it, and its input is 24-bit, output is also 24-bit. Let's make it like that. So we have, so input 23 down to 0, I data, let's have input I control, and we have output 23 down to 0 O data, and we can say like assign O data equal to, if control signal is 1, if control, or you can write control equal to 1, whatever you prefer. O data will be data, otherwise it will be 0. Sorry. Okay, so this is our simple multiplexer. So we need to integrate this also into our block design. So I'm just going here, disconnecting this pin, disconnect pin, and I'm bringing my multiplexer here. Again, I'm just drag and drop, and this is iData, this is our control signal, and this is the output. Okay, so now it should be working. There is no other change. We'll just save the design and configure this as the top module, our system wrapper, and we will, now you can see like everything went inside, right? Your data generator and multiplexer, see, came here, and data generator came here. He found the hierarchy automatically. So we'll just go ahead and run synthesis first. After that, we have to do pin constraint for these signals. After that, we can generate the bit stream. Synthesis is completed. Now we can do the pin assignment. So the clock signal he has automatically assigned to Y19. So the reset signal, since we need an active low, I am not connecting to any push button. I am connecting it to the first slide switch, the dip switch, which is F22. And now you have to give the pins for RGB. So those things we can find from the data sheet, and in the data sheet it is written from lower bit to higher bit. Okay, so this is red 0, this is red 1, this is 2 and 3. So remember to use that order when you're doing pin assignment. Similarly for H-Sync and V-Sync, these are the pin assignment. So let's do it. So I have finished the pin assignment. I have saved all of them in an XDC file, video system.xdc. Now keep the IO standard as LVCMOS 33, because all these pins are connected to the bank or pins of the FPGA where the reference voltage is 3.3 volt. Okay, so change all of them to 3.3. Okay, save that also. Now the only thing left is giving the clock frequency. Now if you go to edit timing constraint, you will find like he automatically detected the clock frequency is 100 megahertz because we did connection automation. So he automatically connected it to Y9, and Vivado knows like on ZedBoard that clock is 100 megahertz. So you don't have to give separate clock constraint. You can go ahead and generate bitstream now. After that we can test it on hardware. Bitstream generation is completed. Now let's go ahead and program the FPGA. So make sure your FPGA is powered up and you have connected a VGA cable between ZedBoard and your monitor. Okay. So this is the output on the monitor. So you can see as we designed 1/3 of the monitor is red, then 1/3 green, and 1/3 is blue. My laptop camera is not that great, that's why the green is not very clear. Now remember one thing, we configured this slide switch as our reset. So if I make the slide switch to 0, my system will go to reset state. That's why the monitor will be blank. So you need to keep the switch at on position to disable the reset. And depending upon your laptop, here I think it's not clear. You can go to the information and you will see like he automatically detects the resolution as well as the frequency. So you can see like he detected it is 1920 by 1080, and vertical frequency 60.1. Okay, so that's about this tutorial. Thank you.